So, very important thing to realize about ionic compounds is they do not form molecules. So, by definition, a molecule is a little self-contained, well, not necessarily little actually, but a self-contained group of atoms that are bonded together. So, this is a water molecule and this is a water molecule. And they are, molecules are actually slightly attracted to each other, but they are separate. They are separate groups of atoms, and they could be the same type of atom, or they could be different. So they could be an element or they could be a compound. For example, two oxygen atoms is a molecule, and that's weakly attracted to another oxygen molecule, but it's not. But you won't get groups of oxygen atoms like this. That doesn't really happen. Whereas with ionic compounds, you do. So a lattice in general is whenever you have this repeated pattern that kind of goes on for as long as is as large as the object is. So if we had a grain of salt, which is sodium chloride, then you have the potassium sodium atom next to the negative chloride atom, and next to that sorry, I said potassium, I meant sodium. Anyway, sodium chloride. So a sodium ion next to a chloride ion, next to a sodium ion, next to a chloride ion, and so on and so forth. It goes on and on and on. It goes on and on in every direction, of course. In fact, I'm only drawing it in 2 dimensions, but it goes on and on in 3 dimensions, in fact. So, so this is a lattice because it doesn't have any particular end. There's no specific end of the lattice, and the formula NaCl doesn't mean there is one atom of sodium and one atom of chlorine. Like this water, the formula for water H2O means it tells you how many atoms are in the molecule. It tells me there are in one molecule. There was 2 hydrogens and 1 oxygen. Whereas this one just simply tells me the ratio. There's a 1-to-1 ratio of them, but it doesn't matter. We don't know how many is in because it depends on the size of the grain of salt. So a lattice do not form molecules. Ionic substances do not form molecules. They form lattices. You can have a covalent lattice. So diamond is an example of a covalent lattice. So you can get covalent lattices like these ones over here. So this one here is diamond. Let's just label these. So diamond. So this is diamond. This is silicon dioxide. This is graphite. And despite the fact that it seems to have a limit, it doesn't actually, in fact. So we could keep on adding to this diamond structure or the silicon dioxide structure, and it goes on and on as depending on however big the diamond is. So a diamond is actually like a single molecule, which is why it's one of the hardest substances. Possibly the hardest substance on Earth still, I think. In any case, that's why it's particularly hard. These substances these giant covalent structures have some quite strange characteristics. So we'll look at in a moment why graphite, for example, is able to conduct electricity, whereas diamond can't. They're both made out of carbon atoms. We'll look at that in a moment. Silicon dioxide, that's still a lattice, a covalent lattice, but made out of 2 different molecules. 2 different atoms. So in this case, going back to what we said earlier on about the NaCl just being a ratio, the same here. SO2, that would be the ratio. It doesn't mean that in this case, despite the fact it's a covalent substance, it doesn't mean that there's one sulfur atom for one sulfur atom and 2 oxygen atoms in every sulfur dioxide molecule, because it's a covalent lattice and it produces. So actually, this time it's the ratio. In the same way, it's the ratio over here. Whereas with water, it's not just a rate, although it is a ratio, but it's also the actual amount in each molecule.